Hello everybody, I'm Anupama. I'm an associate professor in the Department of Electrical Engineering at IIT Bombay. I'm presenting here work done by my student Mr. Kushan Chowksi on use of smart meter data for consumer clustering and demand response program design. We thank the EnergyInformatics.Academy for this opportunity to present our work. Demand side management and demand response are not new terms. DSM refers to activities such as peak clipping, load shifting, valley filling, and promotion of energy efficiency measures so that load shapes can be modified and electricity procurement cost can be reduced. Over the last few years, DSM has taken on a new shape in the form of demand response, where consumers may be sent signals such as price signals shown here on the right hand side of the slide to reduce the grid stress. With demand response becoming very popular in the commercial and industrial demand segment, there is an interest to look at demand response on the residential side as well. There are several home automation solutions that make it possible. For instance, smart thermostats have been used, such as the ones shown here, to reduce the grid stress or grid peak on hot summer days. Plans have been proposed for how EV charging can be implemented to manage the grid load while also reducing the electricity bills for the consumers, or energy efficiency services have been promoted by leading consumer manufacturers as well. While demand response has been hugely successful in the commercial and industrial loads, it has received a mixed bag of response when it comes to residential DR. Here, measures of success can be thought of in terms of tangible reduction in the peak load or significant savings in electricity cost to consumers, or consumers showing eagerness for opting into demand response programs. Our review reveals that urbanization, economy, and other such factors could be responsible for the success of the demand response program. But for us, consumer selection is something that is extremely critical for demand response program design, and this is the aspect we focus on in this presentation. From an academic perspective, with the use of smart meter data, consumer selection can in fact be facilitated. One way to do this is the consumer clustering approach, where consumers can be clustered based on how they are contributing to the system peak, or whether the load behind their consumption is a space heating or a space cooling device, or what is the time at which a specific appliance is being used on the consumption side. The clustering itself could be facilitated through various techniques such as hierarchical clustering or k-means or k-medoids and so on. In this presentation, we will show you how these different clustering schemes could be in fact invoked and how they can be used for demand response program design and consumer selection. One of the ways consumers are in fact partitioned into different clusters is the use of a characteristic profile, which shows how their system load evolves over time for a typical day. A typical approach to define this characteristic profile is to take the time average of the weekday loads. But seasonal behavior may be ignored in this, and whether this profile needs to be normalized or not is unclear. We show here loads, daily load profiles across 10 days for a typical consumer, and we show how this highlights how challenging the definition of characteristic profile may be. This then complicates how the consistency in consumption may be quantified, because the characteristic profile and variations from it are one way to measure the consistency in consumption. Also, how the consumer is contributing to the system peak is based on the definition of this characteristic profile, and a wrong definition here can in fact bias our results. The problem for us then reduces to the following. We are interested in using smart meter data to facilitate consumer selection in a scalable manner. We want to, of course, have meaningful segregation of consumers and have ways through which their interaction with the system peak can be quantified. In this work, we revisit the characteristic profile definition and propose several metrics for quantifying the quality of the clustering process as well as the peak association of individual clusters. And we demonstrate all of this through the use of the Dataport database. The methodology we follow is fairly linear. We take data from about 630 residential consumers in the Dataport database for the 2014 year. This data is processed for filtering data as well as high frequency noise. The missing or bad data is then replaced through the Sarima process, and for each consumer, a characteristic profile is used to cluster consumers using either hierarchical or k-means or k-medoids clustering, and the consumer clusters thus formed are then post-processed to evaluate the consistency in clustering and as well as peak association attributes for each cluster. We take you through all of these steps over the next few slides. We start with how we define the characteristic profile itself. A single consumer's daily consumption profiles are clustered into several groups to identify the typical consumption profiles he may exhibit. For instance, in the plot on the left-hand side, we see that the consumer exhibits three typical consumption patterns shown in yellow, red, and blue. And the frequency of their occurrence is also mentioned. CP1, the yellow pattern, is seen 62% of the times, whereas CP2 is seen 26% of the times, whereas CP3 is seen 12% of the times. A weighted average of these profiles is then used to figure out the actual characteristic profile of the consumer. Our analysis shows that over 40% consumers may actually exhibit at least two characteristic profiles, and this is not uncommon given the fact that weekend and weekday behavior may be very distinct. So this definition of characteristic profile is quite important. The clustering is then done based on the characteristic profiles thus identified for each consumer, and we treat this clustering as a black box, but what is of interest to us is the membership function, whether a particular consumer N belongs to a cluster X or not, and this can take a value between 0 and 1. In a hard partitioning scheme, this value will either be 0 or 1, and we use this to compute the cluster average profile. The mathematics is skipped here to respect the time constraints on the presentation, and I move on to discuss how the clustering process outcomes are then evaluated for consistency measures and peak association attributes. It is very common for the consistency in consumption to quantify the predictability of the consumer is quantified using deviations around the characteristic profile. But for us, we look at deviations in the cluster centroids and then use an average bound consistency metric to compute how often the consumer daily consumption patterns track either of their cluster centroids that we have already identified. This helps us get a better idea of how the daily consumption profiles are in fact similar either to the CP1, CP2 or CP3 patterns that we have previously identified as shown in this example. We then also have a way to find out what the average bound consistency for a cluster or across clusters can be, and this helps us assess the quality of different clustering techniques. Likewise, we also see how a consumer identified to belong to a specific cluster may in fact be grouped in that same cluster based on any new consumption patterns that we see for that consumer. And this helps us figure out the consistency in clustering, both for a specific cluster as well as across clusters. We compare the bound consistency as well as the clustering consistency for three different clustering processes. The clustering process that is based on the average of all the daily profiles, the clustering process that is based on the average of the frequently seen daily profiles, and then our own approach, which is based on the weighted mean characteristic profile that is based on the weighted mean. We see that our process shows a much better bound consistency and a much better clustering consistency. The outcomes shown here are for the hierarchical clustering technique, which seems to have the best Silothe score and is the least affected by normalization. It also demonstrates better consistency performance, and we also notice in paper that our clustering outcomes are sensitive to normalization. Again, in the interest of time, we do not present detailed results here and ask the audience to refer to our paper for more specific details on these remarks. Once the consistency in the clustering is evaluated, we also evaluate the peak association attributes for the cluster. Specifically, in this case, we identified through trial and error 6 clusters are needed to in fact group the 630 residential consumers, and then for each cluster, the cluster average profile is computed and its association with the peak in terms of system peak correlation, system peak magnitude contribution, coincidence, and offset is used to assess the demand response potential. The key challenge here is to in fact compute the duration, and we use the half peak prominence notion illustrated here to compute the duration. We now show how all of the attributes that we have just shown and demonstrated could in fact be used for a meaningful demand response program design. We'll notice for cluster 1 very good consistency performance for the cluster, where the values closer to 1 indicate a good performance. The peak magnitude per consumer in this cluster is quite high, 2.2 kilowatts, and we show that 100% peak coincidence with no peak offset is seen for the overall cluster profile. The cluster profile also has a significant correlation with the system peak demand, making this a conforming cluster that may be suitable for peak pricing schemes. Cluster 3, on the other hand, has slightly lesser of a peak coincidence, with it having a peak offset indicating the peak for this cluster occurs earlier than the actual system peak. Such sort of demand cluster may in fact be amenable to a peak shifting demand response scheme because the consumers may not be so uncomfortable with an early consumption pattern. Likewise, for cluster 6, we see that there is a significant peak coincidence, but there is also a negative peak offset, which means that the cluster peak occurs after the system peak, making it suitable for a valley filling demand response scheme. This cluster also shows the highest consistency in values in terms of both bound and cluster consistency, and hence may be leveraged for a DR scheme. We refer the readers to more details in our paper where all of these remarks are properly summarized. And we conclude this presentation by saying that our analysis conclusively shows that consumers can exhibit several consumption patterns, and it is important for a new set of clustering techniques and metrics to be devised to consider such consumers. We are still working on how to extend this analysis for multi-attribute clustering and for optimal selection of consumers for DR schemes. This is my profile, and I would like to take this moment again to thank the organizers. And if there are any questions, please feel free to reach out to me on the email provided.